Welcome to the third part of a series on some very simple representations of instance, set, and class in the SUMO ontology. In this third part, I'll give you some examples of inferences with the basic information we created in part 2. So I've loaded the statements that we created in the last video, formalizing these couple of examples about instances and classes. And I've added a few more statements. I want to show you how you can do some simple practical inferences with this information. So if you recall from the last video, we had initially a group of 3 humans, John, Mary, and Stanley. We added baby Jimmy, and then later on we lost Stanley. So we want to talk about the elements of this set. So into here, this file, I have added the most basic definition of the predicate element, that it's a binary predicate. It takes as its first argument an entity or anything in the SUMO hierarchy, and its second element, it takes a set. So first, let's define this initial set of John, Mary, and Stan. So it's an instance of a set. It has several elements, John 1, Mary 1, and Stanley 1. As you can see, they're all elements of this set, John, Mary, Stan. Then we'll define a second set. So after the addition of baby Jimmy and the tragic death of Stan, we have a set John, Mary, Jimmy. It's also a set. John is one element, Mary 1 is an element, and Jimmy 1 is another element. And crucially, we do have to say that Jimmy is not an element of the original John, Mary, Stan. And so we have to say this because standard first-order logic doesn't have what's called the closed world assumption. I'll leave a reference to some source material that explains that. But just briefly, it's basically saying unless we know something to the contrary, we can't say that we have complete information. Now, we've said that John, Mary, and Jimmy are part of this set, but we haven't until we make this next statement here that explicitly says Jimmy 1 isn't a member of the set. Then the logic, the semantics of this logical language basically say, well, I don't know. You haven't told me yes, you haven't told me no, so therefore the answer is I don't know. Jimmy could be part of the set, maybe he's not, but we just don't know until we state explicitly that he's not an element of this set. So this can be a little challenging to get your head around, but sort of take it just my word for it or do some research on it. We have to say this. So as our first inference, let's just ask whether these two sets are in fact not equal. So I'm going to go in and ask the query, so query on the highlighted expression, and I get this immediate result. So it's a comparatively simple proof, but again, it's, if you watch some of my other videos, it is proof by contradiction or proof refutation theorem proving, which can also be a little challenging to get your head around. So it basically works by assuming the opposite of what you've asked and trying to prove that that results in a contradiction. And in this case, it actually does. So we take not, this double negation of saying that these two sets are equal. The nots cancel each other out in step 2. The system realizes we need this other element that we've stated explicitly, so that's what this means, that it comes from the knowledge base and gives you a particular line number. So we've stated previously here that Jimmy 1 is not an element of the set John, Mary, Stan. Now, step 4 takes step 2 and step 3 together to reach its conclusion. So it's concluding here that Jimmy 1 is not an element of John, Mary, Stanley, based on this faulty assumption that we've made, because this is proof by contradiction. So we're assuming the opposite of what we asked. We assume the opposite of what we've asked. We're assuming that in fact that these two things, these two sets are equal. And yet we've said here that Jimmy isn't an element of John, Mary, Stan. So if these two sets are equal, John, Mary, Stan, and John, Mary, Jimmy, then we have to say that Jimmy 1 is in fact an element, right, of John, Mary, Jimmy, because they're equal, right? So we have this conclusion here, and yet we also have the opposite statement, because we've said previously in our knowledge base that Jimmy is an element of the John, Mary, Jimmy set. So here we have our contradiction between 4 and 5, and that allows us to prove that if we assume the opposite of our query, we get a contradiction. Okay? So that's proof by contradiction, or refutation theorem proving. So that's one simple inference that we can do with this information. I'm now going to go back to our examples, and we'll do one more simple computation. So we also had the example of this very specific human. Let's call her Jane 1. Right? And she's an instance of this very specific class, Oshkosh human. Now, to do this computation, we're going to need another relationship that we call birthplace that's already defined in SUMO, and I've just duplicated its fundamental elements here. We say that birthplace is a binary predicate, that it takes as its first argument a human, and it takes as its second argument a geographic location. We're also going to say that Oshkosh, Wisconsin is a geographic location, and that an Oshkosh human is a human. And then here is sort of what you might call really the essential bit of the definition of Oshkosh human, that if we have an Oshkosh human, that's this first literal, a logician would call it, in this rule. This is an if-then rule. So this first section says, if we have a variable x, something that is an Oshkosh human, then we can conclude that the birthplace of x is Oshkosh, Wisconsin. All right, we've said that Jane is an Oshkosh human, so what we're hoping the system does is it takes this fact about Jane and it applies this rule, and it's going to give us the answer: birthplace of x, birthplace of Jane 1 is Oshkosh, Wisconsin. So let's just ask that. Essentially here we're asking, what is the birthplace of Jane 1? The birthplace of Jane 1 is variable x, so we're looking to find a binding for that variable. So here we'll do this computation again. We'll go to our plugin menu, query on the highlighted expression, and again here we get a proof. The proof is a bit longer this time. So it includes something called an answer variable, which is a way for the theorem prover to find and give us a binding. You see that here at the top we have that the binding for x is Oshkosh, Wisconsin. Great, that's what we were looking for. And so the deduction says that, okay, this is known from the knowledge base that Jane is an Oshkosh human. This is the rule that we were looking at a moment ago. The theorem provers added in an explicit quantifier here, but for now we can sort of ignore that. I talk about that a little bit in my overview lecture as well as my book if you're interested in the details there. So step 3 here is really directly from the knowledge base. As you can see by this tag here, directly from knowledge base SUMO, line 37. Line 4 is a transformation, a normal form transformation. I've got additional information on my book in that if you're not familiar with it. Basically eliminates this implication sign, and the summary of that rule is that if A implies B, then that is equivalent to not A or B, and that's what we've got here. So you can see how this first part of the rule is essentially A in my summary that I just gave you, and this is B, birthplace, var1, Oshkosh, Wisconsin. So it takes winds up as not A or B. Hopefully you can see that from step 3 to step 4. Step 5 then just reorders the clauses, because or is not specific with respect to order. Then we get the unification, or the resolution, rather I should say, of steps 2 and 5. So let's look at that. So here we've got that Jane 1 is a human, and that's going to resolve with this statement that either the answer is that the birthplace of something is Oshkosh, Wisconsin, or that something is not an Oshkosh human. Well, we know from this step up here that Jane is an Oshkosh human, so therefore for this step 5 to be true, then this must be true, because we know that this part, the negated literal here, is false, right? Because it contradicts this statement up here in step 2. Okay, so now this gives us this intermediate step or lemma that birthplace of Jane was Oshkosh, Wisconsin. And that then gives us a contradiction with our original negated conjecture, right? It's taking the thing that we've asked, what's the birthplace of Jane 1, and automatically assumes the opposite. So it's not the case that Jane's birthplace is something, right? It's a variable. And so that's a contradiction between steps 6 and ultimately the transformation after a couple of intermediate steps of this other statement here. So you can see at the end we get down to 7 gets turned into 8, gets turned into 9. We resolve steps 6 and 9. The birthplace of Jane 1 is Oshkosh, Wisconsin, and that it's not the case that the birthplace of Jane is something. We get this answer variable in here, which essentially just does some unification. I'll maybe cover that in more detail in another lecture. But we do get the contradiction we're asking for. The answer variable unifies with Oshkosh, Wisconsin, and that's what gets us our answer. All right, so this was a whirlwind introduction to some ever so slightly more complicated theorem proving examples than I did in one of my previous talks, and I hope this gives you some idea of how this stuff can be used in practice. And I'll leave some links associated with the video so that if you want to dig deeper, you can. Hope this was interesting for you. Thanks. Thanks for watching this video today. If you enjoyed it, please like and subscribe, and check out the further information at ontologyportal.org, where you can also obtain a copy of my book. Thanks for watching.